What is going on, everybody, and welcome to a quantum computer programming tutorial series. Right out of the gate, I just want to stress I am not a quantum physicist. I know a little bit about things, but I am just not an expert on quantum stuff, okay? I would argue that it seems like nobody really truly is, but I am less so than most, okay, that might talk on this subject anyways. So, my credentials are Python YouTuber, so that should give you a little bit of understanding of my understanding of quantum physics. So with that out of the way, I do want to at least give a basic foundation of quantum, at least in terms of quantum computers. I might say some wrong things, so I encourage you to go out and learn that yourself. I think there's really no shortage of material, even just on YouTube, but just on the internet in general, in terms of concepts and visualizations and just the theory of quantum mechanics and quantum computers. What there's almost nothing of is the actual practical side of things. So that's what I want to come here and do. So first of all, what's a quantum computer? So a quantum computer is just made up of qubits or quantum bits, as opposed to our classical computer, which is made up of bits. So the next question, of course, is what's a qubit? So a qubit is, well, first, what's a bit? So a bit is, in your classical computer, it's just it's a transistor, right? And that can be either a 0 or a 1, and it gets its value from, is it a high signal? So we send voltage through. Either it's a high signal or it's a low signal. If it's a high, it's a 1. If it's a low, it's a 0. So a bit can be a 0 or a 1. A qubit, on the other hand, can be a 0, a 1, or both. Wait, that's illegal. No, I assure you, apparently it can. So it does this through two characteristics that are unique to these quantum bits, which are superposition and entanglement. So the idea of superposition is it is anything it could be, right? And it doesn't actually pick something until you make the observation. So for example, I think the mug is actually a pretty good example, right? Inside this mug, there could be water, coffee, tea, I don't know, hot fudge, all kinds of things, right? And so if this mug was in superposition, it would be all of those things, right? And it's only when we look into it and be like, oh, what do we got? Does it collapse on one of those values? That's the concept of superposition. Now, to me, in my, I don't know, lizard brain, it says, no, there's really only one thing in that cup. So whatever. But I'm just saying, hey, that's the property. The next thing is entanglement. And the concept of entanglement is also magical. And this is kind of if you've ever heard the Einstein's spooky action at a distance, this is what it comes from. So if two qubits are entangled, a change in one causes a change in another one instantaneously, and distance is irrelevant. Again, I agree. That's not allowed. It seems pretty spooky to me, but people much smarter than me assure us that it's not actually spooky action at a distance. We're not violating certain laws like transferring information faster than the speed of light. I mean, that's what it seems like to me. But we are assured that is not it. So anyway, I'll leave the theorizing to other people. All I can say is we have these two properties. How we have them, I don't know. But we have them. So cool. So that's the difference between a qubit and a regular bit. Now, what happens when we have these two characteristics is in a classical computer, the amount of like states that you can represent, right? So each bit has two states that it could plausibly be. It could be a 0 and it could be a 1, right? In a quantum computer, it could be 0, 1, or anything in between. So I hate to say anything, that's incorrect. I would say a 0, 1, or both states. Let's just stick with that, because it's like a multitude. It's not like it wouldn't be a scalar, to my understanding. Anyway, I see the comment section is probably blowing up with some experts. Anyways, what this means to us as programmers on the practical side of things is a classical computer can represent n bits times 2 states. That's it. A quantum computer can represent 2 to the power of n bits states. So this is exponential. This is massive. It's a huge difference, right? So how many states both we can represent, but also like consider. So quantum computers are unlikely to just like replace classical computers. One, because we kind of need classical computers to work with quantum computers, but also it's not that quantum computers will solve all the things that regular computers do or classical computers do faster, right? It's not that. It's quantum computers will solve problems that classical computers can't solve. They just can't. It would just be intractable, impossible to solve, right? Or it would take a really long time, such as factoring numbers when it comes to like factoring for prime numbers. So for example, breaking encryption is one of those things that gets thrown around all the time that quantum computers could do. That's true. So if you're somebody that owns like a database that today, if somebody was siphoning from it right now, in 20 years, if that data would still be highly valuable, I'd be careful if I was you, because probably in 20 years, RSA encryption is Dunions. So these are things we have to think about. I don't really think we're there now, and also, as you'll see, when we actually do the practical side of things, quantum computers have noise and error, and we don't quite yet know how to remedy that. For some problems, it really doesn't matter. For other problems, like breaking encryption, for example, it makes a huge difference. So yeah, so the problems that quantum computers are going to be and currently are and going to be useful for are problems where like the state space is just massive, right? So these exponential things. So a good example to think about is like anytime you have many combinations. So one example that I see gets thrown around by, you know, people that are trying to kind of sell the idea of quantum computers is like logistics. So if you're delivering packages and you've got a route that you need to take, you know, each kind of intersection that you pass is, in theory, a branch that you could have taken. And before long, each turn that you pass or take branches out and creates this just, again, intractable number of other possibilities that you could have taken. A classical computer kind of checks each one kind of in a brute force manner. Sometimes we can use things like gradient descent or you know, something like that to sort of optimize this task. But a quantum computer just simply can analyze all of them all at once, given the correct number of bits. But it doesn't take long to have that correct number of qubits. It doesn't take that long to have enough qubits because it's exponential. So like logistics is one. Another one is like modeling for like molecules. So things in like chemistry. Right now, classical computers can sort of model things, but classical computers, the best thing that classical computer can do is like get close to statistics. We can sort of simulate probabilities, but it's not real probability, right? Whereas a quantum computer, as best I can tell, dare I say, is probability. Like it's true. So that's the difference, right? So another kind of really simple example that I think is easy to fit in one's brain is, like, let's say you're organizing a charity event and you're going to seat people at a table, and ideally you'd want those people all to get along so they're in a nice donating mood. Well, if you have 5 people, then that would be, you know, you've got like 5 seats at a table. The combination of people that you could, like, you know, what combination do you want to seat people? You only have 5 people, but the combinations are 5 factorial, right? So this means it's 5 times 4 times 3 times 2 times 1, right? So that's 120 combinations. But if you just add one more person, it's, because you went from 5 to 6, it's 120 times 6 now, right? So 6 factorial, 720, right? And then let's just jump all the way to like 10 people. It's like 3.6 million. Right? So as you keep just adding just one more option, things get crazy. So these are the types of things that, like, you know, a classical computer could obviously solve for the 120, and the classical computer can do a pretty good job when you start getting to 6 million, or 3.6 million, let's say. But as you continue to go further and further, the classical computer, at some point, it's just not even possible, because at some point you end up having more possibilities than there are, like, you know, atoms in the entire universe. so it's just impossible, right? And so we can prove that already we can definitely have quantum computers that will eventually exceed anything a classical computer could do in terms of large state spaces. Okay, so I think that's really all I really want to talk about in terms of the fundamentals. If you've got questions, feel free to ask them. If I said something silly, feel free to correct me below. Like I said, I'll put some other resources in the description. But let's say you're interested in this stuff. You know, you'll want a quantum computer. What do you do? Well, it turns out, as you might expect, building a quantum computer, I mean, I don't know exactly how much would go into it, but I'm going to imagine that if you wanted to start from scratch, it's probably like at least a $100 million enterprise. You can buy, like I've seen that D-Wave has sold at least one quantum computer for $15 million. D-Wave's quantum computers are different from what appears to me to be everyone else's, and I'm not intelligent enough to explain exactly why, but something tells me that they're questionable compared to the differences are questionable at least. So I'm just going to throw out that they're probably about $100 million device, right? Like so if you Google's 50 qubit quantum computer or IBMs or whatever. So they're expensive, whatever the heck they are. So what do these companies do with them? Well, it turns out they just connect them to the cloud. And anybody can connect and run these quantum circuits on them for free. That's incredible. To me, this seems like it's like the equivalent of like if NASA was like, hey, you can drive the Mars rover, just connect to it and drive it around Mars. That's what it seems like to me. It's just incredible. But I think the thing is, right now we're in a time where nobody totally knows what exactly are we going to use what all can we use quantum computers for. And so it's just like a big kind of experiment right now. So anyway, what a cool time to be alive that we can even play with these machines. So yes, we will play with actual quantum computers as well as simulators. So I think we've got the time. Let's go ahead and set the mood. So first of all, I'm going to be working in the following. I'm just going to have this quantum computing tutorial, and then we're going to install something. So let me get out of the way too. I'm assuming everybody if you're following this tutorial, please know the basics of Python and installing packages. If you don't, I will try my best to put a link to the basics tutorial in the description, but otherwise go to pythonprogramming.net, go to the fundamentals, and learn Python, the basics of Python. You honestly could learn the basics of Python, I feel like in a day. Maybe that's unfair, but days. Okay, so yeah, so cool. So moving on. What we're going to need for this series is some form of pip. I'm going to be using Python 3.7, so really I would say pip 3.7, but depending on what operating system you're on, all that, it's going to vary. But mostly pip install, and then we're going to be using qiskit. That's Qiskit. We're going to use numpy. I'm going to be doing things in a Jupyter notebook, so jupyterlab. If you want to use Jupyter notebook, you can use whatever editor you want. Matplotlib, and then qiskit-ibmq, and then provider. And so if that doesn't give it away, we're going to be using IBM's quantum computers. So there's a lot of providers, like D-Wave has them in the cloud, Google has it, I think, in the cloud, Microsoft definitely does, and then yeah, IBM. I'm sure there's other providers I'm spacing out right now. I kind of poked around everybody's, and honestly, IBM is, in my opinion, the best by far. First of all, you can get set up. I'm gonna be yik-yakking and explaining things, but you could honestly get set up and running in like a minute, or not a minute. Let's say 2 minutes on IBM stuff. So anyway, shouts out to IBM for getting this right. And then Qiskit. I don't know if it's people at IBM who made Qiskit or what, but they seem to be entangled. I'm so cool. So install those things. I'm not going to run it because I've already installed those. Instead, what I'm going to do is jupyterlab. Oh, also, on at least Linux, I found that qiskit-ibmq-provider might get installed with Qiskit, and then it's like, you already have this, it's fine. And then I attempted to use it, and it didn't work. So I needed to do a sudo pip install upgrade force reinstall of that, and I also got a warning about mismatching version numbers. After force installing it, everything was great, but if you have a problem, please let me know. Even though I think IBM's doing a phenomenal job here, all of this stuff is fairly buggy. For what it is, it's awesome, but just expect to need to be patient. I'll also try to put the Slack for Qiskit. Qiskit has like a Slack channel, and at least when I needed help, I got help pretty quick, and it was actually useful help. So anyway, I'll try to remember to put that in there, but yeah, there's so many things to talk about and point you to and stuff, so I might forget something, but if I forget, someone just remind me and I'll put it in there. Anyway, Jupyter space lab to open a notebook. Okay, so let's get this good enough. Okay, so let me name this Qiskit1 or something like that. Obviously, I'm assuming you guys aren't amateurs, but Qiskit1, just name it something that isn't qiskit.py, because, well, actually, it's an IPython notebook. You get away with it, probably. Anyway, just a good idea not to name it exactly the thing that you're going to use. So let us go ahead and get started. But actually, before we get started, you could actually start with Qiskit, but you're going to have a hard time. So I might have to do some blurring if I screw this up, but I'm going to show you guys how to set up. I think because we're going to run on a quantum computer first, but so probably before we get started, the next thing we should do is go to quantum-computing.ibm.com. So let me see if I can just bop over there. Yeah. So you'll have to make an account, and if I think you can just connect to your Google account anyway. I forget how simply I got set up here, but anyway, you'll need to do that, and then you click on this. Oh, my face is on it. Let me do this. Cool. This little account icon. If you click on that and then you go to my account, you'll see you'll have a token here. Hopefully I'm not showing anything else that I should show. I don't think I am. And just click copy token, which reminds me I need to copy over a token. Dang it, I'm gonna have to edit this video. Let me do it. So actually, I might not have to edit this video. So I am going to have my token in a separate file because I just don't want to show it, but you don't necessarily have to do that. I just don't want to end up showing it on camera. So token. So I save mine in a file called token.txt. And then if I go back to where we are, pasta, boom, done. Don't have to edit. Nice. So you would copy that token, and then you would use it in a moment. So just take note, or you could copy it. I think you'll be fine. We won't do any copying and pasting until we need it anyways. So now what we're ready to do is import Qiskit as Q. All of the official Qiskit tutorials that I've seen do from Qiskit import asterisk. I think that's the only thing I would complain about. Don't do that, guys. Stop that. Bad form, bad form. And then matplotlib inline. And Qiskit just simply somewhere along the lines is import. I think when you do your visualization tools, they just import matplotlib, and then this is just notifying Jupyter Notebook to plot inline, like in the actual notebook. So if you are not in Jupyter Notebook, you don't need to type matplotlib inline. Okay, so now we're going to define our actual circuit. So again, with quantum computers, we're working with the bits. So that's how far down we're going. So it's painful as a Python programmer, I know, but we got to start at the bit level. And this is partly why I don't see quantum computers, at least not anywhere in the near term, replacing classical computers, because we actually kind of need to work with both of them. So with what we're going to do here, generally you'll have, Python doing most of your logic or a bunch of your logic, and then for a certain task, you'll pass it through a quantum computer, get your response. So the way it works generally is you're going to define your circuit, right, in Python, and then it's just kind of a representation of the circuit. You pass it through the quantum computer does its thing, And then actually what it does is, even though, so it runs it through, and it runs it through these qubits, and then spits back out the answer, and it spits out the answer in bits, so classical bits. And again, this will make more sense, I think, as we actually work with this. So anyway, I'm just trying to explain as we go. So we have to build these circuits, and these circuits are these like bit circuits. Welcome to CS 101. So q.quantum circuit, and then what we're going to say is 2, 2. Another thing that I kind of noticed was the shorthand here for how to actually get away with this varies. So I've kind of been running through a bunch of different, you know, documentations and stuff like that, and over time this appears to have changed, and it might change some more in the future. But so sometimes you'll just see 2 here, and I'm not sure how that would have ever worked, but anyways, it has worked for me. So anyway, whatever. I guess you could probably get away with 2 if all you were doing was like not actually running it and taking measurements. Anyway, I've personally found that confusing. But what these each value means is basically it's 2 qubits, and then we'll have 2 classical bits. So then what we're going to do is circuit.x. So this is a NOT gate. So we're going to apply a NOT gate to qubit 0. So by default, these bits are going to start as zeros. So we're going to say, okay, qubit 0 not. So we're just flipping it. Okay, so now qubit 0 is so let's say, just to make it super clear, so currently qubit, let's assume these are qubits. It's just a 0, 0. We're saying, okay, qubit 0 not now. So then we're going to say 0, 1, or 1, 0. Trying to help. Now, what we're going to do is apply a circuit.cx. This is a control knot, or a C knot. And this basically, it's I guess maybe the more probably one of the more common ones, and this will entangle the two qubits. So you're going to pass 2 through here. But also what it does is, let me just note it here. So it's a C knot, or controlled knot, and it flips second qubit value if, and only if, the first qubit is a 1, right, or is on, basically. So so we'll CX, and then it's going to be 0 and 1. So in theory, you could actually you could put other qubits in here. We only have 2 anyways. So, but what we're saying, so we flip this. So this circuit now, or this qubit rather, is 1. So already knowing that it flips the second qubit, so it flips qubit 1. If the first qubit is a 1, let's say is a 1, just to be clear. So what will happen, right? So what we should get in return, at least up to this point, right, should be a 1, 1, right? Because we flipped qubit 0 to be a 1. So then what we could say is, we don't have to say this. This again was kind of confusing to me when I was going through things, but we take our measurement. So when we measure, it's important to understand that as soon as you take your measurement, if you did have qubits in superposition, they will collapse into a value. So more on that later, but just know that at this point, now we're actually measuring. We're looking inside the Schrodinger's box with the cat, right? So we're going to see what's in the coffee mug. So we measure, and then, again, I didn't quite understand this, but it slowly began to make sense. We specify the actual qubit register, how it is going to map to the classical bit register. So we're going to say 0, 1 here, and then again, whoops, 0, 1. So it's going to be a direct representation of qubits to qubits to classical bits. What this means is the value after we take our measurement. The value for qubit 0 is what we're going to return for classical bit 0, and then the same thing for number 1, right? So what we should get at this point when we take this measurement is 1, 1 as classical bits. So again, with quantum computers, you take in whatever the circuitry is, right? You're going to probably use a classical computer to build the circuit logically with beautiful programming languages like Python. Then you're going to pass them through this quantum machine, which is going to run this quantum circuit with qubits. And then after we got the qubit answer, we're going to translate that answer back to classical bits so that we can pass that then back to our beautiful Python language and do the next things that we plan to do. For now, we're just building circuits, so that's all we're going to do. So we take that measurement, and then what we can do at this point is there's some really cool methods in here. Whoever made these, I don't know if you're watching, probably not, but whoa. So circuit draw, what we get is a ASCII representation of this circuit. That is really cool. The amount of thinking that goes into making a visualization like this this way is really cool. So awesome job, whoever made that. So another option you have is circuit.draw, and then is it backend? I have to check. Oh no, it's output. I always want to say backend, but it's output equals MPL. This is matplotlib. So now you get a more pretty representation, but I really like this one. Anyway, here is kind of how they denote the measurement. So actually, the first time I was like looking at the actual outputs here, I was a little confused because I didn't know what was this, right? And so this is the symbol for measurement. Same thing here. It's a plus sign rather than, and I'm sure that's coming from historical things, but like, why isn't, like, this is an X, but then a controlled knot looks like this? I don't know. It's a little confusing. But anyway, you can see here, you've got your classical bit numbers here, and then here, I don't know, I just like this one better, I think. But anyway, you can see here, this is our NOT gate, right? And then this is our controlled NOT gate, like it's based on this value here. And then these M's we take in our measurement. Just a nice way for us to kind of see where we're headed. So from here, we can actually run these things through our quantum machines. Now, you can either run it through an actual quantum machine, or you can run it through a simulator. So you would use the simulators just when you're doing R&D, but then when you're actually ready to do your true research, you want to see what the actual answer is, that's when you're going to feed it through a an actual quantum computer. So you can do either of these two things, but I know everybody is going to want to at least try once to run things on a quantum computer. This way, when you're done, you can actually update your resume and call yourself a quantum programmer now. So in order to do this, I'm going to show you guys. And you may follow along, but especially if you're following along on the day of release, feel free to do it, but the queues will probably be quite long. So do what you want. But anyway, what we're going to do is make some space. And what we're going to say is from qiskit, we're going to import IBMQ. And then we're going to say IBMQ dot save underscore account. And then you would put your token in here. So you might even still have it copied, paste it in there. For me, I saved my token to a file. So I'm actually going to say, I'm going to say, one of these days, I'm going to say open token.text, open token text, dude. we need to wrap it up. Token text, and then .read, and then close it all off. Cool. So I can run that. It's going to say the credentials already exist because I've already done this. So you actually only need to do this once. It saves it. So in your other programs, you don't really need to do that. So you only need to run that one time. And then to use it subsequently, just do IBMQ.load underscore account. And there we go. So it's an account. It tells you, hey, this is an IBMQ account, blah, blah, blah. And then now what we can do is actually start working with IBMQ, which is this here, which then gives us access to these following back ends. So continuing along to actually send something to those back ends, what we're going to say is provider, first of all, is going to be equal to IBMQ.get underscore provider. and we're going to say IBM-Q. That's our provider. And then we have a bunch of backends. Now, there's a few ways that we can access these backends. One is you could just look and pick one of these. If we go to the home page, you can see here like IBM-Q Melbourne has a queue of 87 jobs, which is a ton of jobs. I don't know what the deal is. When I was working with this initially, there's like no competition. There was like the queues were all super short, but today it's just going nuts. So interesting. Anyways, and the jobs seem to be taking longer. Like I said, there's a lot of variability here. It's buggy might not be the right word, but patience will be required sometimes. Anyway, IBM-Q, get provider, cool. So now what we could do is for backend in provider.backends, we're going to try, this is going to be a terrible qubit underscore count equals len, backend.properties.qubits. We're trying because one of them is a simulator, except we're not even going to handle the exception. We're just going to say qubit count equals simulated. And then we're going to print, and we'll just make this a nice F string. We're going to say backend.name has, and then we're going to say backend.status, and then .pending jobs queued, and qubit count qubits. Cool. Hopefully that works. No, oh, we spelled qubit wrong. Qubit count. There we go. Qubit. And we spelled queued wrong. Terribly wrong. Let's run that one more time. Okay, so and then simulated, huh? Qubit count, backend properties, did we spell, oh, we spelled qubits wrong again. That's why, qubits. That's why you don't yeah, that's why you don't not handle your exceptions. But anyway, so real quickly, we can just kind of see, okay, well, the Chasm simulator doesn't have any queue, but that's because it's a simulator, so it should run pretty quick, and then I bet they don't even have a queue for it. And then here, we can see, okay, there's 14 queued, 87 queued. We can see immediately when we're actually running our script, and then later, you could even work this in to pick the exact backend right before you want to run, so you get the lowest queue, so long as it has enough qubits. So different ones have different qubits, right? The biggest one available to me has 14 qubits, whereas the rest of them have 5. So at least right now, the lowest queue is IBM-Q Burlington. So we could say, okay, let's use that one. So the next thing that we're going to say is from qiskit.tools.monitor, import job underscore monitor. And what this does is it tells us where we are in the queue and then where we are when we actually go to run the job. So we're going to say backend is going to be equal to provider.get underscore backend. And then we're going to pass the name. So we said IBM-Q Burlington. We'll just go with that one. That's fine. So that gives us our backend. Then we're going to actually say our job is going to be q.execute. And then we're going to execute the circuit that we built. And then we're going to say the backend is whatever backend we chose. And then shots. This is how many times we want to send it through. Because again, every time you take a measurement, it collapses to one value. So we want to send enough shots through to get a decent representation. So I'm just going to say 500 for now. So then, as we run q.execute, it's going to store the job, but we also want to do the job monitor for that job. So let's hope that works. And if it does, I'll probably have to pause and wait as we see what kind of queue I'm in. Okay, we are 4th in queue. Sometimes this runs pretty quick. Like historically, like I said, if I was 4th in line, it would take less than a minute, but lately it's been taking a lot longer. So we will see. I'm going to code at least the next block, and if it's done, then it's done, and if it's not done, I'll probably just pause or something. And then if you're running one, you can either pause or you can just break the current, just hit stop, and then run it on a simulator, and then later come back and run it, maybe when you're going to go eat dinner or something, wait in line and actually run the code. But anyway, so So yeah, so once that actually runs, we end up getting something from the job, which in this case will be a result of, it'll be basically be 500 results, which are just these counts of what are the actual bit values that we got in return. And it'll be 500 examples because we ran this through the circuit 500 times. So now what we're going to say is from qiskit.visualization, we're going to import plot_histogram. And again, just like that ASCII thing, and even this is really cool for matplotlib, like these are all very hard visualizations to make. So I'm really impressed with whoever did all the visualizations for Qiskit, or I assume it was probably multiple people. But anyway, pretty cool. One spot in line closer. So plot histogram, and then from matplotlib, I'm going to import style. You may or may not need to do this. If you're on a dark theme like me, you will. At least if you want to see numbers. And then so I'm going to say style.use, and I'm going to call this dark background. And then we're going to say result equals job.result. So in this case, it will be these like, it'll be a result object actually, but basically what it, like I said, what it is it's going to be a collection of bit values, right? So it should be a collection of, you know, in this case, there's 4 possibilities because it could be a 1 1, a 1 0, a 0 1, or a 0 0. In theory, it really could only be one of those things, but you'll see in a second. So job.result, and then let's do counts equals result.get_counts for the circuit. And then we will do plot_histogram for the counts. And then we'll say legend. Well, we actually don't really need, for this one, we don't need a legend. So where are we in the job? Oh, still in 3rd place. Oh, terrible. And then obviously everyone's job is a little different. So some people's jobs are pretty quick. Like when we go to run this, I feel kind of bad because everyone's going to be running jobs. But our jobs are actually really quick. Like we don't really take that much time to run this little simple circuit. But anyway, so then, anyway, whenever this is ready, we would run this. Now, unfortunately, I'm still 3rd in line. I don't really see any reason to stay here 2nd in line. I don't want to sit for too much longer, but while we wait, I will say shouts out to the recent new channel members. I am sure Chung Chris, Austin Meyer, Deaneria, and Corey Schaefer. Thank you all very much for your support. You guys are awesome, especially Corey Schaefer. If you like Python programming tutorials and you want more, check out Corey Schaefer's channel. If you just type that into search, you'll find his channel. Really good tutorials. So anyways, oh, our job is running. Look at that. Perfect timing. So our job is running. Hopefully we don't get any errors. If you do get errors, is it job.error? Maybe get errors? I forget what it is. There is a way to access your actual errors, but even this job is taking a while. So like I said, I think something's going on today that is making things run a little longer than normal. People, I thought it was quantum computing. I thought it was supposed to be fast. Uh-oh, has successfully Qiskit visualization. I was like, oh no, do we hit an error? Just typoed visualization. Let's try it one more time. Cool, so we get our counts. Now, this is why we can't actually break encryption. So as you can see, the most common response was 1 1, which is the one we were supposed to get. But as you can see, we got some 0 0, some 0 1, and some 1 0. Why is that? We have quantum noise. Notice how everything in quantum physics just sounds awesome. Like this is a quantum tutorial. I'm a quantum teacher. This is quantum errors. But anyway, it's because of noise, and that's actually a lot of noise. My gosh. Maybe that's what's going on. I don't know what's going on if they're like throwing a party in the same room that they have the quantum machines. Who really knows? But they're susceptible to noise, like a change in temperature even, right? So these qubits are stored at like as close to like absolute 0 as possible. It is colder than outer space, right? As far as we know, it's like the coldest place that we know of, which is also nuts, by the way. Anyways, so, okay. So since that took so long, I think the next thing I'm going to do is just run this through a simulator. If you're finding it to go fast, feel free to keep running it through the real backends. Also, if you you can run it either through the backend, you could run it through the actual QASM simulator, which is this one here, or there is the local version that you could run. But for now, I think I'm actually just going to run things on the QASM simulator. So I'm just going to change the backend before I forget to QASM. I don't need to type that. I can just copy it. Copy pasta. And now what I'd like to do is actually change our circuit a bit. So, what I'm going to do, I think we'll just copy what we have up here. I'm just going to copy that, come down here, pasta. So we're still going to be at 2-2. We started by flipping X, but instead what I want to do this time is use a Hadamard gate. Probably butchered his name as well. Anyway, what this does is it puts whatever qubit you pass here into superposition. So now we'll see the result of whether this qubit was a 0 and a 1, depending on how many shots we end up taking. So again, we'll take 500 shots though, just so we do see what the result is. So this one is entangling qubit 0 and 1 together. So we already saw entanglement, but we did not see superposition. And really, superposition is, I mean, they're both pretty valuable, but superposition is the one that's maybe more bonkers. But I don't know, entanglement is pretty bonkers as well. Anyway, so we're going to run them through the simulator. And so we've got the back-end simulator, blah, 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 circuit draw. We take the measurement there. So let's go ahead and draw that circuit, make sure it makes sense. So as you can see, we have the Hadamard gate here, but otherwise you've still got that C0 gate, and then we take our measurements. So the only thing that we flipped is rather than flipping qubit 0, now we're saying actually qubit 0, so when we flipped it, we just said qubit 0 is 1, basically. Now what we're saying is qubit 0 is actually in superposition, and then we're running the rest of the circuit. So that's our circuit. Now we can actually run that on the back end. So again, we're just going to say job.execute, monitor job. So we're actually using the QASM simulator. So we'll still connect, run the job, and then we'll get our result. So I'll copy this, come down here, pasta that. This time, as you can see, we got two major results, either a 0, 0 or a 1, 1. Makes total sense because, again, we're using the C0 gate, and the only time it will flip that second bit is if the first qubit is a 1. So it's either going to be a 0, 0 or a 1, 1. Exactly what we expected. And as you can see, since we used a simulator, it's simulating a perfect quantum machine, which we don't have. But that's why you don't see the other options, because it's simulating as if we had a perfect quantum computer. We don't. So if we were to run this exact same circuit, feel free to if you want, but if we were to run this exact same circuit on an actual quantum machine, we would have found that we got vastly different results, right? Or not vastly different. We would have found that it was 0, 0 and 1, 1 were the highest bars, but we would have also seen some noise. Okay. So finally, just in case, you're on the airplane, right, and you didn't feel like paying $20 for the Wi-Fi, you can also run locally on a simulator. So that's the last thing I'm going to show before I bounce out of here. So the other option is from qiskit-ibmq-provider. So this is your simulator framework for Qiskit. And then we're going to say the sim backend equals air.get_backend QASM simulator. And again, there's also multiple backends here. You've got the QASM simulator, unitary simulator, and then a state vector, I think, but we can also iterate over them. So I'll do that real quick. So we could say for backend in air.get_backend, backends, print backend. Derp get backends. Really? What did I do wrong here? Air.get backend. Is it back? Oh, I tried to do the same thing before. Okay. So we've set our sim backend to already be the QASM simulator. But as you can see, you get state vector and unitary. So again, this is what represents and is most closely like the actual quantum machine that you're going to use, right? You're going to pass it through a quantum machine, and each time you make one pass, you get one measurement, right? Things can be in superposition, but as soon as you take a measurement, that superposition collapses down to that value, right? So you're going to pass 500 times. So the return you get from the QASM simulator is going to be counts for however many shots you passed. State vector, on the other hand, you could actually just pass one time. What you'll get back is all of the possible states, right? Because it's a simulator. Okay, so one thing to take into consideration, though, is if you're actually working on real quantum-like problems, the state vector simulator is going to be a problem because you're going to have to store all of the states in memory. So the whole point of quantum machines is so we don't have to do that, or that we're going to solve problems that we can't do that on a classical computer. So this is really cool, and it comes with a bunch of extra visualization type stuff that we can do. Same thing here. They're all really good. But the QASM simulator is most closely related to what we're actually doing here. So anyway, so once we've got the sim backend, again, we can run all of these exact same things. So I'll just take this pasta, and then rather than backend, we'll say sim backend. And then we'll do this. Boop. Wait for it. Because we're running 500 shots, so don't forget. And again, our simulator locally is also perfect, so we don't have any error. So we only get 0, 0, and 1, 1. But, okay. I'd say that's enough. It looks like I've been recording now for 46 minutes. That's a good introduction to quantum computers. Like I said, not an expert, but there you go. Moving forward, I don't know how long this series will be, when the next video is coming out. I'm going to keep tinkering around. I think it's really cool. It's a completely new paradigm. It's a new way for us to have to think about computing. So it's just really interesting to me, and I also think it's just awesome that you can run things on a real quantum computer. Like I said, I find it similar to if NASA let you control the Mars rover. So anyway, really cool. To continue along, like I said, I'll put some further resources in the text-based version of this tutorial. Also, if you just go to that quantum-computing.ibm.com and then click the little thing that looks like a Jupyter notebook, you get start here, and that has a bunch of links to further information. There's also a textbook that I link in the text-based version of the tutorial. Why are you taking so long? Thank you. It's got a whole bunch of information here. I would at least, if you really want, you can go through all of this kind of stuff here. And then there's the advanced ones. So you've got advanced and fundamentals. There's a bunch of stuff. There's just so much information. And like I said, I think IBM's done a really good job of just getting all this stuff out there and making it really quick and simple to get running, right? So yeah, pretty cool. Also, again, things might be buggy. Also, if especially the day I release this video, chances are the queues are going to be massive. You might want to wait. You might just want to use the simulator and then run it later or something like that. But okay, that's all for now. Questions, comments, concerns, feel free to leave them below. Come join us in the Discord. That's discord.gg/centdex. Again, thank you to the new channel members, and I will see you guys in another video.